In this problem, we are given two very long line charges charged with opposite sign charge placed on the distance 2a between each other. And it needs to find electric field lines for this charge distribution. So electric field lines would be the equation, and they are drawn to show the electric field for the charge distribution and to illustrate the electric field. And it can be found from the potential, scalar potential of this charge distribution, and the potential will be the sum of these two potentials. And if taking a look from above on this charge distribution, and then having 2-point charges from the top of, from this viewpoint, then the potential surfaces, equipotential surfaces, which show the potential of each charge, are these concentric circles around the charge, and electric field lines, which are parallel to electric field, the actual electric field, are perpendicular in every point to the equipotential surface, and the direction is from plus to minus. So here is the illustration of electric field of this charge distribution, and we can find the potential, scalar potential. In pink pages is given potential of the line charge on the page 6. And in our case, with this x-axis chosen to be the distance between the rods, then we would have here plus minus a. Total potential would be sum of those two potentials and now the square root can be taken out of the brackets, taken out of the natural logarithm sign, and now we can transfer to cylindrical system of coordinates, because in this case, if we continue solving, we will come to expression which is large and is difficult to proceed with. So having this circular shapes, forms, it would be easier to transfer to cylindrical coordinates. You can try yourself to solve this part and then to see why it's actually difficult in rectangular system of coordinates. So from x and y coordinates to r and phi. So I will write this part inside the natural logarithm, because because this part is independent from rectangular coordinates, and then I will open this bracket. So here x square and y square is r square, and x square and plus minus 2a. So x can be presented so this projection would be the r times cosine phi. So now I will write the potential, scalar potential in cylindrical coordinates and continue. So should be like that. Yes, to be correct. So, oops. So the next step, we can write the gross electric field found from the potential minus grad phi. And now we need to introduce some line, electric field line, which would be parallel with electric field. So let's say for cylindrical coordinates it's on R. So it's a segment of the electric field line. And now we can write it for cylindrical coordinates. So for cylindrical coordinates, there is r in phi direction because phi is dependent on r also. That's by definition of line, segment of line in cylindrical coordinates. From other side, the electric field will have in two-dimensional space, it will have radial component and angular component. So now if we equalize one side to another, well, and also we can write for the gradient again in cylindrical coordinates, phi has this 1 divided by r in the definition of gradient. So let's equalize this. for each component. And if we divide one on another, we bring R to one side, and then unit vectors will begin. So we got such a relation, which is a equation for the electric field line. However, I forgot to write the proportionality constant. So actually dr and E are related through proportionality constant K. I'll write it here. So why this proportionality constant is needed? Because of the density of the line. So if the charge is strong, then the illustration of the electric field is with a dense line, and if the charge magnitude is smaller, for example, then it's the density of the electric field lines is shown with less lines. So this is this proportionality constant, which helps to take into account this moment. So this proportionality constant then would be accounted here, for example. Right? In radial direction, it would be K times radial electric field. The same for the phi direction. But here, when we write the equation of electric field lines, so the relation of one to another, K is gone. So it doesn't influence, it's just a proportionality constant. So from here, we can find the electric field, the radial and the angular component, and how we can find it through the scalar potential. So let's find each component of electric field minus d phi dr in r direction. So it needs to take a partial derivative in r direction. Oh, not in r direction. Derivative over r. So that's a constant, and this part I will write separately and plug it in then in there. So this natural logarithm r minus Okay, so logarithm 1 divided by this, and then the derivative of this 2r minus 2a cosine phi minus this will be and now I will open the brackets. So this was only for this part. There will be this numerator that will just continue below. Minus minus plus, and then minus minus. All this has the same numerator, so let's cancel. This is equal to this, and this is equal. I can write up here where I started this. solution. So will be bottom will be this. And for the top, so this is 4 minus 2 is 2, and minus 2 again. Yes, so we'll be left 4r squared, 4r squared a cosine phi. And here, minus 2 and minus 2 is 4a cubed cosine minus. So something can be taken out of the brackets, like 4. And then a cosine can be also taken out of the brackets. Minus a squared. That's for the radial component. Now for the angular component. So now derivative d phi and then r and a square are not important. The bottom is the same, and the top is different. Minus cosine will be minus sinus, so sinus phi, and the rest is the same, 2r. And here, is a plus, right? Yep. And then here is minus sinus phi. And now I open those brackets. So So this and this getting cancelled. And the rest just summed up. I don't know if I made a mistake, could be. Two and two. No, it's different. This and this, yes. Anyway, 4 y plus 4 ak. 4 a r sinus y can be taken out of the brackets. And left is r squared plus a squared. Let me check if it's correct. No, it's actually correct. So just the thing to write it down. And then I go for the numerator. Minus here and the minus for the potential is here plus. And here we also have 1 divided by r. So this one seems to be with, no, again, minus with minus, yes. Again, plus. Divided by r. So 4 and r can be cancelled. And that's what is left. Yeah. Seems to be good. So, and now we divide the E magnetic field and radial by electric field and angular. So we divide one on another. It's gone. A is gone. This large things are gone. And what we have is cosine, sine, and that expression. This, and it's equal to okay, and now we simplify and bring bring r to one side of the equation and phi to another. Cosine divided by sine is cotangent. So that's what I got so far. It should be R. Yeah. And now using the formula for differentiation, I can find, so I can differentiate these two. Here's plus. Yeah. And for the cotangents is natural logarithm of sinus plus proportionality constant k. Proportionality integration constant k. So that's it. So there's two. That's the answer, basically, for cylindrical system of coordinates. No, seems to be correct. So first we can rewrite it back to rectangular system of coordinates and get expression which would look like circle equation.